Welcome. My name is Matt Wright, and I'm here to talk to you today about the multipole expansion of the electric potential. Now, we have been learning many different ways to write down the electric potential and ways to find it. We did Coulomb's law, we did Laplace equation, we did Gauss's law, which you can't find V directly, but you can find it indirectly, right? And now we're going to talk about making an expansion. So what we're going to do is we're going to take our V as a function of R, and we are going to expand it in the following function. We're going to expand it with some term that's going to go as 1 over R, right? And then we're going to expand it as some term that goes as 1 over R squared. And then we're going to have another term that's going to go 1 over R cubed, and so on. So the farther you are away from some charge distribution. So if this is my charge distribution, if I'm really far away, say at point P, right, I can look at a situation where 1 over R cubed may be 0, but 1 over R squared isn't. So what I'm going to do for the next few minutes is I'm going to take our potential, I'm going to expand it into this form. And what's great is that this form has a physical meaning. This term is going to be as if it's approximately a monopole or single charge. Now, if you're at the train station, right, and you look at a train, its lights on the front of the train look something like this as it's coming towards you. But if you look at that train from very far away, you only see that, right? You see one light. You see one light, right? Because if you're far enough away from those 4 lights, what you see when you look at it is just one light source, right? It's approximately like it's one light source. So we call that the monopole moment, right? It's as if we're looking at some charge distribution. All we see is the effect of adding up all the charges, right? So then the next term is going to be the dipole term, right? It's going to be, look, so here it's like a single charge, and here it's going to be like a double charge, right? Where it's like a positive charge and a negative charge, right? So it's going to be a double charge. And then there's going to be the quadrupole, right? And then the octupole, and so on. So this is the quadrupole is like there are 4 charges, right? And so this is a really exciting thing, right? So remember what I was talking about before. If I have a monopole, it's like looking at the train coming at me, even though there's a whole bunch of lights. I only see one light when it's very far away because all those lights merge into one from my perspective, right? Of course, as it gets closer, we can start to see that there are, in fact, more lights on that train. So looking for a dipole can be thought of as looking at structure, right? So if I look at a monopole from very far away, it just looks like one thing. But if I start to see dipole happening, it's like there's some structure in the object. And so that's kind of exciting, right? So one of the really cool experiments that's happening right now, really trying to understand string theory, and one of the possible cool experiments that can tell whether or not string theory exists or doesn't exist, is trying to look at the dipole of an electron. So if there's string theory or some other exotic theory that explains how particles work, then at some point we would expect there to be some structure, right? More than one light inside an electron. But so far, we've only measured that there is one charge, one perfectly amazing electron-y charge from the electron. So we would like to have more so we could try to understand it. There'd be some interesting stuff in there, be very exciting. We're at the cusp of trying to figure out whether or not it's string theory or something else. It's really super exciting. One of our former students is working on this for his PhD. All right, let's now take our potential and do some expanding. Okay, so if I have a charge distribution, right, and I'm at some point P here away, I can write down my potential as 1 over 4 pi epsilon naught, the integral of rho d3x over script r. Right? Just the standard Coulomb's law that we know and we love. Right? If I have my origin is here, I have some arbitrary element of my charge distribution here, call that r prime. We have the r vector that goes to point P like we've been doing all along. Right? Our script r runs between the two. Right? And then the angle between them we're going to denote as alpha. So if you look at this, it's like, oh, that's kind of ugly, right? So we can figure out what script r squared is by using the law of cosines, right? It's going to be r squared plus r prime squared minus 2r prime cosine alpha. I can factor out an r squared, right? Because we know this point P we're saying is going to be long, very far away. It's like we're looking at that point where the train is going from like where you see one light to seeing maybe more than one light, right? So this becomes okay. And of course we're looking at the 1 over that, so what we really care about is 1 over script r, right? Because we're going to plug it into that. So what we really care about is 1 over r, 1 over 1 plus r prime squared over r squared minus 2 r prime r cosine alpha. Okay. So that's, to the 1/2 power, right? Because if I take the square root of this, I take the square root of that too. That's kind of a nasty beast, isn't it? Right? So we're going to do a couple of things to kind of clean it up and make it a little bit easier. First thing we're going to do is we're going to take it and write it over here because we're going to need it later on. So this r, this is the integral over the prime coordinates. So this r is actually going to be a constant when doing that integral. So I can pull it out of the integral. And I get the integral of rho 1 over 1 plus r prime squared over r squared minus 2 r prime over r cosine alpha to the 1/2 power, and then of course d3x prime. So it's still nasty, right? But let's see if we can clean it up a little. So the first thing we're going to do is we're going to call r prime over r, we're going to call that x, right? So we can rewrite this 1 over r, so 1 plus x squared minus 2x cosine alpha to the minus 1/2, right? And then we're also going to call this term here, we're going to call that epsilon. So we have x squared minus 2x cosine alpha. So what we're really caring about is doing the expansion on the following equation. So we're going to take that and we're going to expand that for near epsilon being 0, right? Because we're going to be in a situation where r prime over r is very small, right? Because r is at point P, and this is very far away. Again, we're looking at the train. Well, the train so far that it's only just one light. Okay. So, let's take f of epsilon is equal to 1 plus epsilon to the minus 1/2. Right? So if I go ahead and look at the point when f of 0, I'm plugging 0 in, I get 1. Now I take the derivative of this, because I'm going to do a Taylor expansion. So I get minus 1/2, 1 plus epsilon to the minus 3/2. I go ahead and I plug in f of prime 0, and I get minus 1/2. I continue. F double prime of epsilon is minus 1/2 times a minus 3/2, 1 plus epsilon to the minus 3/2 power, minus 5/2 power, right? And so if I plug in 0 here, if I plug in 0, I'm going to get a positive 3/4. All right, so if I do this again, for the third derivative, I'll stop after 3, don't worry. You get minus 3/4 times, plus 3/4, minus 5 seconds, 1 plus epsilon to the 7/2, and that derivative, that's going to give me what? 15 over 8? Negative 15 over 8, right? So if I have this equation here, and I expand it, it's going to be approximately 1 plus the first value, sorry, getting ahead of myself, the first value plus the first derivative times epsilon plus 1/2 the second derivative, evaluated 0, epsilon squared, plus 1 over 3 factorial, the third derivative, evaluated at 0, epsilon cubed, and so on, right? So if I take these and I go ahead and plug them in, you get 1 minus 1/2 epsilon plus, now I'm going to take 1/2 times 3/4, 3/8 epsilon squared. Now this is a little tricky. 3 factorial is 3 times 2, so that's going to be 6 over 15/8. Let's see, that's going to be minus 5/16 epsilon cubed plus dot dot dot. Why? So the 3, you're going to get 5 because the 3 is going to cancel out the 5, but you're still going to have a 2 left over, so 2 times 8 is 16. Okay, now you have to take in what you know about epsilon and plug it into this equation. All right, so let's do that. Sorry, of course there's a r to the minus 1 over all of this, right? Because what we really care about is the 1 plus epsilon to the 1/2. All right, so the first term is 1. So the second term is minus 1/2 times epsilon. This is what epsilon is. It's x squared minus 2x cosine alpha. Okay. Then you have plus 3/8, right, times epsilon squared. And what we have is epsilon 2x cosine alpha squared. And then, of course, minus 5/16 x squared minus 2x cosine theta cubed, and so on. Okay? So, let's reduce it some more. Ugh, it's such a pain, right? So remember that x is equal to r prime over r as we work through this problem. Okay. So, let's now go and expand this out some. So 1 plus epsilon to the 1/2 is equal to 1. Now I'm going to have plus x cosine alpha. So I looked at this term first, minus 1/2 x squared. So I flop them because I kind of know what's going to happen next. Next, I'm going to take this and I'm going to square it. So plus 3/8, and I'm going to have x to the 4th minus 4x cubed cosine x plus 4x squared cosine squared alpha. Okay, now I'm going to do the same thing here. So I'm going to have minus 5/16. Now I'm going to do the squared to the 4th minus 4x cubed cosine alpha plus 4x squared. Shoot. This is a total disaster, right? So I have, if I'm going to do this cubed, I have x squared minus 2x cosine alpha times this squared whew, that's nasty. Okay, so I can reduce it some more. So this becomes 1 plus x cosine alpha minus 1/2 x squared. Now I have plus 3/8 x to the 4th minus 3/2 x cubed cosine alpha plus 3/2 x squared cosine squared alpha. Right? That's just getting through here, and then I can do some more arithmetic here. Minus 5/16. This times this is x to the 6th. This times this is x to the 5th cosine alpha. This times this is plus 4x to the 4th cosine squared alpha. Right? Now we do the other term. This times this is minus 2x to the 5th cosine alpha plus 8x to the 4th cosine squared alpha. Now, the last term, which is going to be minus 8x cubed cosine cubed alpha. And now you can see something interesting happening, that as I go to higher and higher orders, the lowest term is x cubed here. So in my third term, the lowest power of x is cubed, right? So that gets a way of keeping track of some of these quantities. All right, so let's distribute through again and see if we can clean this up even more. 1 plus x cosine alpha. And now I'm going to go ahead and group my x squareds together. So I get plus x squared 3/2 cosine squared alpha minus 1/2. That's interesting. Right? And now let's get the cube term. So minus 3/2 x cubed cosine alpha, and then plus 3/8 x to the fourth. That's really interesting, huh? All right, and now if I start going through these, 5/16 x to the sixth, so minus 5/4 x to the fifth cosine alpha. Wait, sorry. I can clean this up some more because I have this term and this term. That's going to give me -6, right? So that's going to give me minus 30/16, right? 6 times 5. X to the fifth cosine alpha. This term and this term, I can add them together, I get 12. So that's going to give me plus 5 times 12 divided by 16, x to the fourth cosine squared alpha. And of course I have the final term here, which is going to be plus 5/2 x cubed cosine cubed alpha. Okay. All right, so now let's group the x cubes together and see what happens there. 1 plus x cosine alpha plus x squared, 3/2 cosine squared alpha minus 1/2. And now my third term is going to be plus x cubed, right? 5/2 cosine cubed alpha minus 3/2 cosine alpha plus dot 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 of higher orders. And so you start thinking about it, well, wait a minute. This is just P0. And this is just P1. And this is just P2. And this is just P3. Holy cow! This is just the generating function for the Legendre polynomials. So 1 plus epsilon, so the 1 over script r, right? 1 over script r is equal to 1 over r times the sum from L equal 0 to infinity of the Legendre polynomial L as a function of the cosine of alpha times r prime to the L power times r to the, or divided by r to the L power, right? So that here, right, remember this is in terms of x, and I know that my x is r prime over r. So that allows me to have this summation here, right, where my x's are getting higher, or r prime over r squared in power, right? And here I have my Legendre polynomial, so that's also increasing, and that allows me to write this in this form. So what? Well, now it does something amazing. Woohoo! All the crazy math goes away. And we're left with this nice frickin' expansion here in our potential. 1 over 4 pi epsilon naught r times the quantity of the sum of L equals 0 to infinity, right? And now what I have is I have my rho, which is my charge distribution, times r prime to the L power over r to the L, times the Legendre polynomials in terms of this weird alpha, cosine of alpha term, and the integral d3x prime. So now I've taken my potential and I've expanded it. The first term here is when L equals 0. right? We have V equals 1 over 4 pi epsilon naught R, and we get the integral of rho, making all of these 0, d3x over r to the 0. Right, so the first term simply looks like the charge. Okay, that makes sense because that would be the monopole moment. All right, what's the next term look like? Okay, it's when L equals 1. So I have plus the integral of rho r prime PL. So that's just PL1 is just the cosine of alpha, right? Because the first Legendre polynomial is x. Integrated over all space, divided by r. Well, crap. This just looks like the dipole moment. See the next video. Over r. So this is the dipole. And so on. I can't wait to do example problems in class with you.